Good morning. So in previous class we discussed about different types of data types, right? For example, we have to discuss parameter, we have to discuss value set, we have to discuss register, we have to discuss wire. Like this we have already discussed. So let us continue with respect to what data types. Next one is system task and directives we have to discuss in today's class. So system task, it's similar to C programming, and we also discussed directives with different types of directives are available with respect to Verilog. System task, so many system tasks with respect to a Verilog HTL, but here we have to discuss few system tasks. So here we discuss only 4 system tasks here. So we have to display the result, we have to monitor the result, we have to monitoring a signal, and also we have to stop the operation, we have to finish the operation. So these are all the 4 system tasks we have to discuss in next session, and also we have to discuss 2 directives here. 2 important directives is enough for this syllabus. First, let us discuss about a system task. So here in so many system tasks with respect to a Verilog HTL. So one by one we have to discuss here. The first one we have to consider here. The first one is display. Okay, so here display is very important one. So before going to display, what do you mean by system task? So here in Verilog HTL, Verilog provides some standard system task in for routine services. Okay, so let us consider here a display is the one system task and monitoring is another one, then start and stop. First one we have to consider a displaying information. So how to displaying the information? So here the system task is always start with a dollar symbol. It's always start with respect to dollar symbol, and also after the dollar symbol we have to write the what? A keyword. So this is the what? A syntax. So here dollar keyword. Keyword may be a display or a monitor or a finish or a stop. Okay, one by one we have to discuss here. So first one let us consider here. Here in displaying information we have to display the what? A string or display the parameters. So let us consider a syntax for displaying information here. When you write dollar symbol, after you have to write a display. Okay, this is the what? A keyword for displaying the information. So using this keyword we have to display the what? A different results or different parameters. Let us consider example. Here this is the example for displaying the result. So usage, it's not a keyword, okay, but here dollar symbol or dollar display is the what? A keyword for displaying the information. So this P1, P2, Pn, it may be P1, P2, it may be a string, or we have to write the string with respect to what? Double quote. So it may be a parameter, so it may be a constant, or it may be a register. Okay, so we have to display the what? A information. That is the what? Display information. So let us list the what? A different string format specification. So here we have to discuss some important formats regarding displaying the information. So let us go one by one. First one, percentage %d, or you can write %d. So both are what? A same meaning. Either you can use a small d or capital D. So again it depends on the a programmer. So here what it indicates, that is the question here. So it indicates display variable in decimal. So when you put the what? this one percentage D or percentage D, so it indicates a display variable in decimal format. So second one we have to consider here. So B or capital B, so it indicates display variable in B indicates it's in binary one. Okay, again we will discuss with an example, this example later. Okay, these are all the format we have to discuss here. So next one, S, small s or a capital S. So it indicates display string. So next one we have to consider here, C or capital C. So it indicates display ASCII character. So we are familiar with this ASCII, that is American Standard Code Information and Interchange. Okay, so sometimes you have to use a ASCII character. So that indicates a capital small c or capital C. So next we have to consider H. So H, it indicates hexadecimal, that is a display variable in hexadecimal. Okay, again just go to next one, V or capital V. So it indicates it display the what? Strength. So it display the strength. So next one, that is small t or capital T. So it's very important one, because in Verilog HTL our main aim is what? A calculation with respect to a time only. So that's why here T indicates time. So it indicates display a time. So time may be, it may be a nanoseconds or it may be a microsecond. Next one we go to important one, that is small e or capital E. So it indicates display real number in, very important thing, scientific format. So it's very important one. So percentage E or percentage E, that is a alphabet. So display the real number in scientific format. Okay, scientific format, for example here 3E10. Okay, so this is the example when you represent the what? A scientific form. So next move on to a percentage F or percentage F. So here same here, okay, both are belongs to a real number, both E and F, but here we have to display the real number in a decimal format. Okay, that is the speciality of a percentage F. That is last one we have to discuss, G or percentage G. So here it indicates you can possible to display a decimal format, or it may be possible to display a scientific format or any other format. So that is the what? A speciality of G and G. So this is the what we are to displaying the result. These are all the what? Format. So and display. So these are all the what? Important formats. These are all the examples we have to consider at displaying a results. So results may be a string, or it may be some time, or it may be some value we have to discuss here. So one by one, here different types of examples. We can't what compare, we can't what represent one by one. So we consider one by one here. First one, display the string in quotes. This is the what? Comments. So our aim is what? Display the string in quotes. So here dollar display. So this is the what? A keyword with respect to what? Displaying the information. So this is the keyword dollar display. So what is the display content here? Hello Verilog world. So here display content is allow Verilog world. So we have to display the allow Verilog world. So after this execution, after this line, so it display what? Allow Verilog world. Okay, so this display is what? It's displaying information keyword. It's similar to a printf in a C programming. So this is the first example. Second example. So display the value of current simulation time 230. Indicates it's nanoseconds. Okay. So here what's our aim? Display the value of current simulation time 230. So here dollar display. So dollar time. So dollar time we already discussed in previous one, that is during data set. So it indicates dollar time indicates it calculates the what? Current simulation time. Okay, so that's why you put what? Dollar time. So that is what is the current simulation time? 230. So after this line it display the what? 230. So next different one we have to consider here, display value of 41-bit address. This is the example 1FC 000010, that is 1C at time 200. When the time is 200, so it display the what? This information. So before you display the information, we have to store the what? In terms of a register. So register 0 to 40 virtual address. So name of the what? Register is virtual address here. So what is the what? Display content. So dollar display at time percentage D. We already discussed the percentage D is what? It's a decimal one. Either you write small d or capital D. Okay, here. So percentage D virtual address is in terms of hexadecimal. That is H indicates what? Hexadecimal we already discussed. So here we have to display the what? Decimal as well as hexadecimal. So time is what in terms of decimal? Then hexadecimal. So here next dollar time. So it indicates what? A current simulation time. So in that clearly mentioned we have to display the what? Current time, current simulation time. So virtual address is what? The name of the register. So after execution this at time. So what is the time? That is we mentioned already, that is 200. So at time 200. Virtual address, there is no change in virtual address, is then address is what? We mentioned here 1FC 00001C. Final result is at time 200 virtual address is what? This address. Okay, this is the another representation. That is next is specialty one. Okay, up to this one we have to display the what? A character or time and as well as some addresses. So next one, display the X character or it may be display the Z character. X means we already discussed is an don't care, Z means it's an I impedance. So here display the value of 4-bit bus 10XX in binary. Our aim is what? Display the value of 4-bit bus 10XX in binary. So before what you display the result, first we have to store the 4-bit address. So reg, that is register, 4-bit address, name of the register is what? Bus. So what is the information we have to display here? Dollar display is keyword, bus value is percentage B. Okay, so here it clearly indicates you have to display the data in terms of a B. So what is the binary value? That is the question here. So bus value is a 10XX. So this is the what? Some example regarding a displaying the information. Next, once you display the information, you need to monitoring that information, right? So next, monitoring information. So the keyword is $monitor. So representation is $monitor. These are all some examples. Usage $monitor P1, P2, Pn. So P1, P2, Pn. So it may be a variables or it may be a constants or it may be a strings. Okay, depends on the examples. So here in $monitor. So why $monitor is more special compared to a display? Because here you have to monitor the what? A current information. So here the specially for you have to monitor the current simulation time because it's very important one. So using this $monitor we have to monitor the what? Current simulation time. Again I repeat, when the value is changes, okay, when current simulation time is changes, and that time it monitors as well as display the information. So that is the specialty of $monitor. So here usually there are two tasks with respect to a $monitor. One we called as a dollar monitor on, another one is we called as dollar monitor off. So why it is required? Because of here it's specially designed for a simulation time. In simulation time, here sometimes we have to enable the what? A simulation time, and that time we are using dollar monitor on. Sometimes we have to disable the what? A that is simulation time. So on that time we are using dollar monitor off. These are all the examples with respect to dollar monitor. So here our aim is monitor time and value of signals, clock and result. So we have to monitor time and value of clock and signal. So we have to monitor time as well as value. So next, here what is the aim for displaying monitoring the result? So here monitoring the time and value, then what is the agenda of this one is clock toggles every 5 units. Means every 5 units time, that is 5 nanoseconds, the clock is toggle, then and reset goes down at 10 time units. So it indicates the clock is changes every 5 nanoseconds, then reset is goes down every 10 nanoseconds. That is the aim. So we have to write the what? A dollar monitor, using dollar monitor here. First, before starting the what? A dollar monitor, first we have to initialize the what? That dollar monitor. Initial begin, its keyword here, initial begin, then dollar monitor, then dollar time. We already discussed. So dollar time, it indicates here we have to calculate the what? Current simulation time. So that's why we have to write it what? Dollar time. You simply write the time, and that time we can't calculate current simulation time. So time we can calculate, but we can't calculate current simulation time. So once the what? Mention the time, the value of clock is equal to binary. Okay, so he clearly mentioned the result should be what? Clock result should be binary, as well as result reset should be what? Binary. So what are the display content? Clock and reset is the what? A display contents here. So when it is 0 nanoseconds, what happens? The value of signal is clock is equal to 0 and result is equal to 1. So this is we have to assume here, okay, when it is 0. So after 5 units or after 5 nanoseconds, what happens? What's the condition here? Every clock toggles every 5 units. So here earlier clock is equal to 0, here clock is equal to 1. But there is no changes in reset, because here it's an up to what? 5 units or 5 nanoseconds. So next we have to consider a 10 nanoseconds. When it is 10, he clearly mentioned. So again it applicable. Clock toggles every 5 nanoseconds, and as well as reset goes down to what? 10 time. So here the variation between the 5 to 10 is what? 5 nanoseconds. But variation between 0 to 10 is what? It's in 10 nanoseconds. So after 10 nanoseconds, so clock is earlier is 1, then it becomes in 0, because the clock is what? Toggles every 5 nanoseconds. Yeah, this is the very important thing. So earlier reset is equal to 1, he mentioned reset goes down at 10 time. So here at 10, then reset goes to what? 0. So these are all the what? Example regarding a monitoring information. So next, first the system task is displaying information. So second one is monitoring the information, right? So once you display and monitoring, we need to what? Stopping, we need to stop the simulation, as well as we need to what? Terminate the simulation. Let us consider one by one, stop and finish. The first one is stop. So here the syntax for stop is a dollar stop. So it indicates you have to what? Stop the programming. So why stop the programming? Because sometimes we have to what? We want to debug a programming, right? We want to debug, or we want to modify some changes with respect to programming. So on that time we are using a dollar stop. So next, dollar finish. So dollar finish, it indicates we have to what? Completely terminate the program. That is, the program is completed. On that time we are using a dollar finish. So dollar stop, so it stop the programming. If you want a debug the programming, so debug the program and then continue the what? Program. So here if you want terminate the program, on that time we are using a dollar finish. So let us take examples for a dollar stop and dollar finish here. So here our agenda is what? Stop at time 100 in simulation time, so and examine the result. So we want to stop the program and examine the results. That is our aim. Then finish the simulation at time 1000. So first at 100 nanoseconds we want to stop the program. Then at 1000 nanoseconds we want to what? Terminate the program. So here initial begin, it's the keyword for Verilog HDL. Initial begin. Then here we have to assume the clock is equal to 0 and result is equal to 1. So before the clock and result, here first we have to initialize the what? Time is equal to 0. Okay, that is first, that is default one. We have to initialize, we have to write the initial means we have to what? Default, the time is equal to 0. So after this hash 100 $stop. So it indicates this will suspend the simulation at time is equal to the 100. Okay, when it is 100 nanoseconds, the program has been stopped. Then if you want debug or if you want some changes, we can modify the what? Program. So after this hash $900 finish. So it indicates this will terminate the what? A simulation time is equal to 1000. Be careful regarding this one. Here 100 nanoseconds, stop the programming. So 100 plus 900, 1000. When it is 1000 nanoseconds, finish. So this indicates what? This will terminate the simulation time when time is equal to 1000. So next, last topic of the part A, first half of the module. So compiler directives. So here so many directives are available with respect to Verilog HDL, but here we have to discuss a few compiler directives here. So one we have to consider, first one define, second one include. So here the question is how to represent the what? A compiler. So the compiler directive can be represented as, so this is backtick then keyword. So compiler directive can be represented as backtick and keyword. So here there are two compiler directives. One is backtick define, another one is that is backtick include. Backtick define, it's similar to what? Hash define in C programming. It's similar one. So include is similar to what? Hash include in C programming. So here first we consider backtick define. It's used for, we have to define a particular text in Verilog HDL. So it means when you consider a compiler substitutes a text of macros wherever it needed. So wherever you needed the what? The text, and that time we have to consider a tick define. So let us take example here. So here the first one, define a text macros that defines the default, it's in word size. So wherever tick define is you include, and that time the size is what? It becomes in word size. So let us take define word size 32. So wherever the word size is appear, and that time it indicates it's in 32. Again one more example. So define as $stop. So $stop you already discussed in previous session, that is a $stop indicates it's stop the programming. Okay, if you want debug the what programming, you can possible to debug. So here it indicates wherever S appears, and that time the program has been stopped. So here last one, define word register reg 31 down to 0. So it's a 32-bit register. So wherever word register is there, and that time the 32-bit is replaced. Okay, these are all the examples for a define. So second one, include. So here the name indicates we have to include a program in another program. Okay, so wherever include the program with respect to another program. Let us take one example, then you can easily understand the what do you mean by include. So include the file header.v which contains declaration in main Verilog file design v. So it indicates we have to include the file name is header.v to to another file. So what is the name of another file? That is design.v. So in example, backtick include header.v. So here backtick header.v file is include in what? A design.v programming. So this is the example for including. So these are all the compiler directives with respect to Verilog HDL. So next move on to what? A part B, that is modules and ports. So next, module and ports. So this is the what? A second part of the second module. Modules we already discussed in previous module, right? That is previous chapter. In previous chapter we have to define the module, that is just a definition of the what? Module. Here we have to discuss in detail about the module, and also ports. Ports is very important topic, because here we have to define the what? Ports and some rules and regulations of ports, then how to define the what? Port declaration and some hierarchical part. It includes the what? Modules and ports. So this is the what? A block diagram for modules representation. In Verilog HDL, divided into three parts. First part is you have to define the name of the module. Then in second part, it declares the what? Specifications of the programming, that is specification of the circuit. Then finally end the what? Module. So coming to what? The first part. So in first part, module, the Verilog HDL is always start with the keyword module. So here you have to mention the name of the module. Then port list. So port list means what are the inputs and outputs are available, that mentioned in port list. Then port declarations. Once you mention the port list, what are the inputs and outputs are available in port declaration. If available, at that time you have to mention the port declaration. So if you want some mention the parameters are optional one. If you want parameter, then mention the parameters. That is the first part. So here the second part is you have to mention the logic. So it's divided into 5 parts. So in first part, declaration of wires, registers and other variables. Okay, here you have to mention other than inputs. So other than input means the wires, we call it as intermediate signals. Then registers, that is specially used for in behavioral description. Then if you want other variables, sometimes you have to mention real variables, then some decimal numbers is there, so you have to mention other variables. Then second part, data flow statements. So data flow statements is always start with what? Assign. So you have to mention the assign statement before the data flow statement. So that is the one type of description. So next one, instantiation of lower level modules. So this is belongs to a gate level description. So we have to instantiate the different modules. For example, we have to consider full adder. In full adder there are 2 instances. Means we have to write using 2 of adder, we have to design the full adder. It's just an example for a gate level description. So next one, always initial blocks all behavioral statement. So we know that we already discussed behavioral description. So behavioral description is what? It's a high level description language. So here we are using always is predefined word for with respect to Verilog behavioral description, and the initial we are using here. So this is the what belongs to a behavioral description. So after this what? Declaration of registers, wires, if it is data flow, if may be gate level, it may be a behavioral description. Next you have to mention task and functions. So what are the tasks required for data flow, behavioral and what? Gate level description. Here we have to mention here. After mention the what? A different types of description. So once the task and functions is completed, next end module. Using end module we have to what? End the module. So this is the what? A block diagram for module definition. So let us take example for modules. That is previously we have to discussed. So let us take SR latch is the example for the module definitions. So here S means set, R means reset. So here we have to consider latch. We know the definition of latch. Latch is what? It's a temporary storage element. So we have to write the SR latch using universal gates. So better we choose a NAND gates here. So there are two NAND gates for SR latch. So here universal gates, so it indicates it's always complement, right? So that's why the input can be declared as S bar, another input is declared as R bar. So obviously the SR latch two outputs Q and Q bar. So this is the what? A final diagram for SR latch. So here based on this one, so we have to write a Verilog HDL code. So in this one we have to assume a gate level description for the what? A better programming. Okay. First it's always what? Start with module. That is Verilog HDL is always start module. The name of the module is given as underscore latch. Okay, then next we have to declare the what? Ports. List the ports. Then after we declare the what? Different ports. So what are the ports available here? That is S bar, then R bar, then Q bar. So next we have to declare in terms of a ports definition. So there are two ports available with respect to this diagram, that is input port as well as output ports. So what are the input here? Input is S bar and R bar. So you have to write S bar and R bar. Okay. Next, once you declare the what's inputs, next move on to output. Output, what are the outputs here? One is Q, another one is Q bar. So any intermediate signals required with respect to this? No, there is no intermediate signal is required for this SR latch. Directly we go to what? Instances. So how many instances here? Obviously two instances. One is NAND gate 1, another one is NAND gate 2. Next, so there are primitive gates is available with respect to what? Verilog HDL. So that's why we directly mentioned the what? Primitive gates, that is NAND. It's the predefined word. NAND is the predefined word. The name of the first NAND, you name it as N1. This one, okay, that is first one. So N1 in bracket. So there is a rules and regulation with respect to gate level description. Again we discuss in detail in later modules. But here, what are the outputs here? First you have to mention Q is the output. Then what is the input here? When Q is the output, what is the input? So obviously S bar is the input. So what is the another one? So be careful, Q is the output, then one more is Q bar. Okay, that is the what? NAND 1. NAND 2 can be written as N2. So what is the output? Q bar is the output here. What is the input? R bar is the 1, another one is, so that is Q. So next, once your instantiation is completed, then end the program, that is end module. Again I repeat this. So module, that is name of the module given as SR latch. Then list, you have to list the inputs and outputs. So S bar, R bar, Q and Q bar. S bar, R bar, Q and Q bar. Then input S bar and R bar. Okay, these are all the inputs. So here the specialty of Verilog HDL. So when you write the what? Output mentioned here, it takes both output as well as input. Means instead of output we can possible to write in out. Okay, but you mention the output, it automatically takes both input or output. Okay, that is in out. So output Q bar. Next, NAND. There are many primitive gates available in Verilog HDL. So out of this we are using this one, that is NAND gate. That is NAND is the predefined word. So first one, that is we have to consider here. What is the output? Q is the output. What is the inputs here? S bar is the one, another one is, that is fed back, that is Q bar. Next one, NAND. Second one, N2, then Q bar is the output. then R bar is the input and as well as Q. Then once you done the what instances, next end the program, that is end module. So here up to this one a design part. So we have to write the what SR latch code. So here up to end module, this is the what a design part. Next move on to what, once the design block is completed, we have to what, check the program. So how to check the program? So that can be done by a stimulus block. Okay, so stimulus block or also we called as a test bench code. So here module, that is name of the module is top, or also we called as a name of the stimulus is top, that is TOP. Then here wire Q comma Q bar. So here output acts as a what, Q bar. Then here wire, it means it acts as a output here. Okay, register acts as a input, wire acts as a output. So here you have to mention same name or different name. Okay, try to mention different name, because on that time you can understand which one is the stimulus, then which one is the what, a design parts. So that's why here you have to write small q and q bar and also a different name compared to what previous one. That is here you have to mention S bar and R bar. Here we have to mention set and reset. So once you mention the what, wire and register, this is very important part, because here the instantiation part, okay, both stimulus as well as design, that can be done by here SR underscore latch M1. So here say it should be same name, S underscore R underscore latch M1, here Q. So here how many inputs and outputs here? There are 4 inputs and outputs. You have to mention here Q bar. Be careful here. That is inverter of set. Why? Because of here we are using an AND gates. Okay. So that's why you have to mention inversion of set. Here also inversion of reset. So once it is done, next we have to put what? Some data here. Next, data is always start with the keyword initial, then begin. So here $monitor. Why $monitor required? We already discussed in previous session. So it monitors the what? That entire data. Okay, that's why we are using $monitor. Here $time. So it indicates we have to what? Mention particular simulation time. If it is simply time means it's continuously running. Okay, so that's why you put $time. It indicates the particular simulation time. So set is equal to %b. We already discussed %b means set is equal to data in terms of binary and reset is also in terms of binary. So q is equal to %b. Obviously the q is what? The binary data. Okay, once you mention the word binary data here, then output is also binary data. So here slash n, it indicates new line. Okay, we already discussed in previous module, that is in data type, that is slash n indicates a new line. So in new line it have to display set, reset, q, and if you want then display the q bar. So q bar is sometimes it's not required. So that's why we neglect the q bar here. So you have to display set, reset and q. So once its monitor is been done, you have to apply the data. Set is equal to 0, reset is equal to 0. That is initially set is equal to 0, reset is equal to 0. So after some nanoseconds, after 5 nanoseconds, reset is equal to 1. So initially 0, 0, after as 5, that is 5 nanoseconds, set is, there is no change in set, that is 0 only, reset is equal to 1, then there is a begin, end, then end module. So this is the what? A test bench or stimulus program for the SR latch.